Hi everyone, so welcome to Entry app, and we are going to start the next topic, that is basics of vectors. So in the previous lecture we have seen the introduction part, and in this lecture we are going to start with the basics of vectors. So I have already told that so for the next few lectures we are going to build some mathematical foundation, so in order to understand this subject in a crystal clear manner, right? Okay, so in that process our first topic in basics of mathematics is nothing but what? Is nothing but basics of vectors, right? Okay, here. So now see here. Okay, so in nature any physical quantity can be categorized into two types. One is a scalar quantity and another one is what? A vector quantity, right? 1 minute here, right? So in nature any physical quantity can be categorized into two types. So one is what? One is a scalar quantity and another one is nothing but what? Is nothing but a vector quantity. So one is a scalar quantity and another one is a vector quantity. So I hope you know the definitions for scalar quantities and vector quantities. Yes or no? Okay. So there is no need to write the definitions and all. So you know that what do you mean by scalar quantity here? So a physical quantity which is having only magnitude but not direction, then we call it as what? We call it as a scalar quantity. See, physical quantity means which is the quantity which is measurable, that is called as physical quantity, right? Okay, here. So a physical quantity which is having only magnitude is called as a scalar quantity. It is not going to have any direction. So that's what we call as scalar quantity. And what do we mean by vector quantity here? So the quantity which is having both magnitude as well as what? As well as direction. Then those type of quantities we call them as what? We call them as vector quantities. So these definitions you are very much familiar, right? Okay, here. So this is going to have only magnitude. It is going to have only magnitude. It is going to have both magnitude as well as what? As well as direction, right? So we know these definitions here. We know these definitions, right? Okay. So now here I am going to give you some examples. I am going to give you some examples for scalar quantities and some examples for vector quantities. So just we will write the examples for scalar quantities here. Examples. So the examples are nothing but mass, temperature, volume, mass, temperature, volume, distance, speed, work, or I can say energy, work or energy, right? And then voltages and current, etc. So these are some of the examples for scalar quantities. What are the examples here? Mass, temperature, volume, distance, speed, work or energy, voltage and current. So these are some of the examples for scalar quantities, right? So similarly we will write some examples for vector quantities here. We will write some examples for vector quantities, right? So the first example I am giving here is nothing but force is a vector quantity, right? Next, surface area. So throughout our subject we are going to consider the surface area as a vector quantity, right? Whereas volume is what? Volume is a scalar quantity, whereas surface area is a vector quantity. So we are going to see all these things here. As we proceed into the subject we are going to see all these things one by one, right? So force, surface area, and then displacement, velocity, right? Okay. And here I have told mass is a scalar quantity, whereas weight here, weight is equal to what? Weight is equal to m into g. Yes or no? So g is nothing but acceleration constant, Yes or no? Okay. So g is nothing but acceleration constant. So this acceleration constant is going to have what? Is going to have direction. Yes or no? Acceleration is a vector quantity, isn't it? Okay. So if it is a vector quantity means weight is also what? Weight is also a vector quantity, right? Okay. Okay. So next. Next, so mass is a scalar quantity, whereas weight is a vector quantity, because here z is nothing but acceleration due to gravity, right? So acceleration due to gravity, acceleration is a vector quantity, g is a vector quantity, and hence weight is also a vector quantity, right? Okay. So force, surface area, displacement, velocity, and then weight, and then I can say electric field. I can say electric field is a vector quantity. Magnetic field is also what? Magnetic field or H field. Okay. Magnetic field or H field is also what? Is also a vector quantity. And then one more example I can give is current density. One more example I can give is current density, right? Which is represented with say bar. So current density is also what? Is also a vector quantity. So etc. etc. So these are some of the examples. These are some of the examples for vector quantities, right? Okay. So the examples for scalar quantities are mass, temperature, volume, distance, speed, work or energy, voltage and current, etc. Whereas the examples for vector quantities is force, surface area, displacement, velocity, weight, electric field, magnetic field and current density, etc. Now if you observe here, here I am saying that the current is what? The current is a scalar quantity, but here I am saying that the current density, whereas the current density is a vector quantity. Okay, current is a scalar quantity, whereas current density is a vector quantity. So we know, do you know the relation between the current density and current here? See, the relation between current density and current is nothing but, see here, Z bar, the current density Z bar, okay, or I can say the current I is equal to, I can write it as what? I can write it as surface integral Z bar dot dA bar. So this is the relation between the current and current density. Right. So here Z bar is a vector quantity. So dA bar represents a small differential area. So this small differential area is also a vector quantity, and you are doing here vector operation. So that is nothing but dot product. Okay, and we know that the resultant of dot product here, the resultant of this dot product is nothing but what? Is nothing but a scalar quantity. Is nothing but a scalar quantity. So which means the current is nothing but what? Resultant of this dot product. Yes or no? Double integral dot product of Z bar dot dA bar, this results in a scalar quantity, which is nothing but what? Which is nothing but current. So which means the current is what? The current is a scalar quantity, whereas current density here is nothing but what? Is nothing but a vector quantity. Now if I assume if I assume Z bar is independent, Z bar is independent of integration variables. If I assume Z bar is independent of integration variables. So here dA bar means you are going to have two integration variables. Yes or no? It may be like dx, dy and dy, dz, like that. Understood? Okay. So you are going to have two integration variables. Right. If suppose this Z bar is independent of integration variables, then we can treat this Z bar as constant. Then this Z bar will become constant with respect to this integration variables. So in that case, I can write I is equal to what? So if it is constant with respect to this integration, then you can take it out of the integration. So then I can write it as Z bar dot what? Dot double integral dA bar. So this one I can represent it as what? This one I can represent it as Z bar dot double integral dA bar will represent the total surface area. So that is nothing but Z bar dot A bar. right? So the same expression I can represent in this manner. So here J bar dot A bar is nothing but what? This is the dot product between the current density and the surface area. If you observe here, the current density is a vector quantity and the surface area is also what? Is also a vector quantity, and we are doing the vector operation, that is dot product between these two vectors, and the resultant of dot product is nothing but what? Is nothing but a scalar quantity, and the resultant of this dot product is nothing but current, and hence current is what? Current is a scalar quantity. Current is a scalar quantity. Understood? Okay. Okay. So current is a scalar quantity, whereas current density is a vector quantity. And one more thing, see here, see, whenever, if you are having two vectors here, if you are having two vectors, so let us say if you are having here F1 bar is equal to the magnitude I am representing, let us say F1 bar is equal to 4 newtons. Okay, just I am representing the magnitude, 4 newtons along this direction. Let us say here you are having F2 bar which is equal to 3 newtons, right? The phase shift between this F1 bar and F2 bar is how much here? 180 degrees. So now in this case, what is the resultant force here? What is the resultant force? Tell me. What is the resultant force you are going to have? See, F1 bar is acting in this direction, that is 4 newtons, and F2 bar is acting exactly opposite direction, that is 3 newtons. So the net force, the magnitude of net force will be equivalent to what? Will be equivalent to 1. Will be equivalent to 1. I am writing only magnitude here. Right. So here the net force magnitude is equivalent to what? Is equivalent to 1. So 4 newtons is acting in this direction, 3 newtons is acting exactly opposite direction. So the resultant force or the net force acting at this point will be equivalent to what? Will be equivalent to 1. Right. Next, similarly, if I consider F1 bar is equal to 4 newton. Here I have considered F1 bar equal to 4 newtons, and here I have considered F2 bar is equivalent to what? 3 newtons. Now here the angle between these two vectors is how much here? 90 degrees. Right. So in this case, what is the resultant force here? What is the resultant force? So how to calculate the resultant force? The resultant force is nothing but what? Just draw a parallel line to F1 bar and draw a parallel line to F2 bar. So the resultant force is going to point in this direction. So this is nothing but what? F net. Right. So this is nothing but what? This is nothing but 3 newton, and this is nothing but 4 newton. So what is the resultant here? What is the magnitude of the resultant force? Is equivalent to what? Square root of 3 square plus 4 square. 3 square plus 4 square, which is equal to what? Which is equal to 5 newtons. Which is equal to 5 newtons. Here it is 1 newton. Okay. So here you are not changing the magnitude of the forces. Yes or no? Here you have taken F1 equal to 4, F2 equal to 3. Here also you have taken F1 equal to 4 and F2 equal to 3. You have not changed the magnitude of the forces. What you have changed? You have changed only the angle between the forces. So whenever you are changing the angle between the forces, the resultant force is also changing. Understood? So this is called as vector addition here. This is called as vector addition. So whenever you are adding any two vectors, or I can say simply the vector addition is going to depend upon what? It is not only depending upon the magnitude, it is also depending upon what? It is also depending upon the angle. Okay. So whenever you are adding any two vectors, okay, so you have to consider the magnitude of the vectors, and also you have to consider the angle between the vectors. So this is very, very important, right? Okay. So whereas in case of scalar addition here, right? So just we are going to add the magnitudes. Yes or no? We just, if I say simply 3 plus 2 is equivalent to what? Is equivalent to 5. If you write 2 plus 3 also, it is also equivalent to what? 5. Okay. It doesn't matter how you are adding. So it is simply scalar addition. It depends only upon the magnitudes, right? Okay. Okay. So that is the difference between the scalar addition and vector addition, right? Okay. So one point here you have to remember is vector addition that means whenever you are adding any two vectors, it not only depends upon the magnitude of the vectors, it also depends upon what? Angle between those two vectors. So that is very, very important. And one more point here you have to understand here is one more point. So you can make a note here, you can make a note. Okay, so how to take the angle between any two vectors? This is very, very important here. How to take the angle between the two vectors? See, suppose if I am having, let us say I am considering this vector f1 bar. Let us say this is f1 bar, right? Next, I am considering another vector. Let us say I am considering another vector f2 bar, f2 bar, right? Okay, or I will draw in this manner here. So here I am considering f1 bar, right, and here I am having f2 bar, f2 bar. Now I want to determine the angle, okay, or I want to measure the angle between f1 bar and f2 bar. So whenever you want to measure the angle between f1 bar and f2 bar, what you have to do is you have to join the tails of what? You have to join the tails of the two vectors. First, what you have to do? You have to join the tails of the two vectors. So without changing their direction here. So f1 bar is horizontal direction like this, f1 bar, right, and f2 bar is pointing in this direction. So f2 bar is like this, right? Okay, so rough diagram I am drawing, that's it. So this is f2 bar. So first of all, you have to join the tails of what? The tails of f1 bar and f2 bar. You have to join the tails of f1 bar and f2 bar. Right. So once you have joined f1 bar and f2 bar tail to tail, then you have to measure the angle. See, this is, you can measure the angle like this. Yes or no? You can measure the angle like this, or you can measure the angle between f1 bar and f2 bar like this also. Yes or no? So this also gives you the angle between f1 bar and f2 bar, and this also gives you the angle between f1 bar and f2 bar. So which one you have to consider as an angle between these two vectors? See, always remember that the angle between, always whenever you are measuring the angle between any two vectors, you have to consider the least possible angle here. So this is the least possible angle between what? Between f1 bar and f2 bar. You always consider, you have to always consider the least possible angle as the angle between these two vectors, any two vectors. Understood? You should not consider this one, right? If so, you should not consider this one, you have to consider this one. Whenever they have asked what is the angle, suppose this angle is theta dash. If suppose they have asked what is the angle between f1 bar and f2 bar, you should not say theta dash, you have to say theta. Understood? Okay. So how to measure the angle between any two vectors here? Always you have to join the two vectors tail to tail, and then you have to consider the least possible angle between the vectors as the angle between the two vectors. Okay. See, for example here, for example, you can take one or two examples here, right? For example, see here, if I consider a vector, let us consider a vector f1 bar here, right? Okay. Okay. So next next I am considering another vector. I am considering another vector like this. Okay. So this is f2 bar, right? So I have considered f1 bar and I have considered f2 bar like this, right? And this angle is let us say 60 degrees. This angle is, let us say, 60 degrees, right? So this angle is, I have given as 60 degrees. Now if suppose, if anybody asks what is the angle between f1 bar and f2 bar, if you say 60 degrees, if you say it as 60 degrees, that is wrong, that is wrong. Why are? So what I have told, whenever you are measuring the angle between any two vectors, what you have to do? You have to join the tails of the two vectors, then you have to take the least possible angle. Understood? So here they have given it as 60 degrees, and if they ask to determine the angle between f1 bar and f2 bar, what you have to do is without changing the direction here, you can redraw the figure in this manner. So f1 bar is pointing in this direction. So f1 bar is pointing in this direction. right. Now F2 bar is pointing in this direction. So without changing its direction, just shift this F2 bar, such that the tail of F2 bar has to touch what? Has to touch the tail of F1 bar. So just shift this vector. Okay, see, you can move the vectors here, without changing its direction. Understood? That is called as parallel shifting. Okay, so if you move the vectors without changing its direction, is called as what? Is called as parallel shifting, and this parallel shifting is allowed whenever we are dealing with the vectors, right? Okay, so just move this vector here, just take this vector and move this vector in the same direction, such that this tail of F2 bar will coincide with what? With the tail of what? With the tail of F1 bar. So you are having like this, right? Okay, so previously you are having the vector like this. So this is F2 bar they have given, and here they have given this angle as what? They have given this angle as 60 degrees. But whenever they ask the angle between F1 bar and F2 bar, you should not say 60 degrees. What is the angle? You have to shift this F2 bar like this, which is called as parallel shifting. Without changing its direction, you can move the F2 bar from this location to this location, such that the tail of F2 bar will coincide with what? Will coincide with the tail of F1 bar. Now, what is the angle here? What is this angle? So this is the least possible angle. Yes or no? This is the least possible angle between F1 bar and F2 bar. So this you have to tell as the angle. Between F1 bar and F2 bar. What is this angle? See, this total angle from here to here is nothing but what? Is nothing but 180 degrees. So this is what? This is 60 degrees. So if this is 60 degrees means this angle theta will be what? Theta will be 120 degrees. So here you have to tell the angle between F1 bar and F2 bar as what? As 120 degrees. So this is the right answer, right? So this is how you have to measure the angle between any two vectors. So why I have told this point here? Because whenever you are adding any two vectors, right? So the addition between any two vectors is going to depend upon the angle between those two vectors. So if you don't know how to measure the angle between those two vectors, then there is a chance that you are going to do the addition of vectors in a wrong manner. So that's why I have explained all these things, right? Okay, so these are just basics here. I hope you have understood this clearly, right? Okay, yeah. So here I have just simply explained some briefly about the vector quantities, right? Okay. So vector addition is going to depend upon the angle between the two vectors, and I have explained how to measure the angle between the two vectors, right? Okay, fine. Okay. So one more point you can note here. You can make a note one more point here. So that is so all vectors must obey vector law of addition. All vectors must obey what? Vector law of addition. All vectors must obey vector law of addition. Understood? Okay. So I have told already how to add any two vectors. So whenever you are adding any two vectors, so the addition between the vectors will always depends upon the angle between those two vectors. So it is very much different. Vector law of addition is very much different from scalar law of addition, or you can simply say scalar addition. Understood? Scalar addition is very much different from vector addition, right? You can simply write it as vector addition, right? So if it is a vector quantity means it has to obey the vector law of addition. So here vector law of addition means here the addition between any two vectors is must depend upon what? Must depend upon the angle between those two vectors, right? Now if I take for example if I take a current here, so let us take here one resistor here, and here another resistor, right? And here I am considering another resistor. So let us say this is R1 and this is R2 and this is R3, right? Now here let us say the current that is flowing here is I1, and let us say the current that is flowing here is I2, and here the current that is flowing is I3, right? So now here if you apply the KCL at this node, what you are going to write? So I1 plus I2 is equivalent to what? Is equivalent to I3. So this is just what? This is just a scalar addition, isn't it? This is just an scalar addition. It is not vectorial addition. So I can say that the current is what? Here also I am proving that the current is a scalar quantity because it is simply following the scalar addition. It is not obeying the vector addition. Yes or no? Here the addition between these two I1 and I2 is not depending upon the angle between these two branches. Yes or no? So whatever may be the angle between these two branches, here I1 plus I2 is equivalent to what? Is equivalent to I3. So which is nothing but what? KCL. So this is simply an algebraic addition, or you can simply say a scalar addition. Okay, it is not a vector addition. So since it is following the scalar addition, so we can treat the current. The current is always what? The current is always a scalar quantity. So throughout our subject here, we are going to treat the current as what? The current as a scalar quantity. See, why I am specifying here is generally the students have this confusion whether the current is a scalar quantity or vector quantity and all these things. So that's why in order to clarify all those things, I am specifically talking about this current. Okay, I have proved here also, and previously also I have proved from the relation, that is I is equal to J bar dot A bar. From this relation also I have proved that current is a scalar quantity. Current is a scalar quantity, right? Okay, so from here onwards you should not have any doubts about the current. Whenever anybody asks what is the current, current is a scalar quantity, right? Okay, so right, so this is all about the scalar quantities and vector quantities, scalar quantities and vector quantities, right? Okay, fine. Next, so next we will see vector addition here, vector addition. Okay, how we can add two vectors. So that's what we are going to see here, vector addition. So here we can perform the vector addition through graphical approach. We are having two approaches in order to perform the vector addition. So one is what? One is a graphical approach, and the second one is a analytical approach here. The second one is nothing but analytical approach. So in a graphical approach, I hope you have studied in your high school about this triangle law of addition, and parallelogram law of addition. Okay, so these are the vector additions that we are going to perform through what? Through graph, that is graphical approach. We call it as graphical approach. Okay, so analytical approach means here we are going to add the two vectors. Here we are going to add the two vectors with the help of what? With the help of the formula. So we are going to develop the formula in order to add the two vector quantities. Okay, so by applying the formula, if you add two vectors, then we call it as analytical approach, and if you add the two vectors with the help of this graph, then we can call it as what? Graphical approach. So I hope you know this triangle law of addition and parallelogram law of addition. So I will give you some brief view about this triangle law and parallelogram law of addition. So triangle law of addition here. So I hope you know these things, so that's why I am going to give you some brief overview, that's it. Okay, there is no need for us to go in detail about this triangle law, parallelogram law and all these things. Okay, so just I will give some brief view about this addition. So if you are having a bar, vector a bar, and if you are having some vector b bar, right? Okay, so if you want to add these two vectors with the help of triangle law, then what triangle law says is take this vector b bar, okay, so without changing its direction, so it is pointing in horizontal direction, so without changing its direction, join the tail of b bar to head of what? To head of a bar. So without changing the direction of B bar, join the tail of B bar to what? To head of A bar. Now join the tail of what? The tail of A bar to what? To head of B bar. So this is going to give you, join the tail of A bar to head of B bar. This is going to give you the resultant vector C bar, which is equivalent to what? Which is equivalent to A bar plus B bar. So this is the triangle law of addition. So this is graphical approach. Okay, we are having another one. So that is a parallelogram law of addition. Parallelogram law of addition. Okay, so here what you are going to do? So let us assume here we are having an object here. Let us assume here we are having an object. So on this object, let us assume two forces are acting simultaneously on this object in two different directions. Let us assume two forces are acting on this object simultaneously in two different directions like this, right? Okay, so in that case, what is the resultant force? What is the resultant force acting on this object here? So two forces are acting simultaneously on this object in two different directions. So in order to determine the resultant force direction, you can apply what? Parallelogram law of forces. So what this parallelogram law says here? What this parallelogram law says? So just draw the parallel line to F1 bar and just draw the parallel line to F2 bar. Okay, so this is F1 bar and this is what? F2 bar. Now the resultant force is given by what? The resultant force is given by the vector that is pointing from this point to what? To this point. So this is the resultant force, or I can say net force. Net force on this object is going to act in this direction. So here this net force acting on the object is equivalent to what? Is equivalent to F1 bar plus what? F1 bar plus F2 bar. Okay, so you know these things also, that is parallelogram law of forces, right? Okay, yeah. So whenever two forces are acting simultaneously at the same point in two different directions, then in order to get the resultant force direction, you can apply parallelogram law of forces. So what this parallelogram law of forces says? So just draw the parallel line to F1, just draw the another parallel line to F2. Now draw the vector that is pointing from this junction, that is from this point to this one. So then it is going to give you the net force. So that net force will be equivalent to what? Will be equivalent to F1 bar plus F2 bar. Right. So this is a parallelogram law of addition. So this is the graphical approach here. This is the graphical approach in order to add any two vector quantities, isn't it? Okay. Okay. So here you have to make one more note here. Here you have to make one more note. So write down the note. So note is nothing but, see here. Now if you are having the vector, let us say this is A bar, and here you are having another vector B bar, and here you are having another vector C bar, and here you are having another vector D bar, and here you are having another vector E bar, right? Now, so another vector E bar, right? Now here if they ask us to determine the expression for C bar, right? Here you are having what? Here you are having multiple vectors, yes or no? Okay. So here you are having multiple vectors like this, right? So now here, see here, always remember that, see here. So if you start from this point here, if you start from this point, you have started from this point, right? And you have moved along this closed path. You have moved along this closed path and again reached to the same point, right? Then what is the net displacement here? If you start from this point and you have moved along this closed path and again reach to the same point, in this case what is the net displacement? So in this case the net displacement is equivalent to what? Net displacement is equivalent to 0. Yes or no? Starting point is this one, and also ending point is also this one. Starting and ending point is the same point. So in that case the net displacement around this closed path will be equivalent to what? Will be equivalent to 0, Understood? So from this, what we can conclude here? What we can conclude? So the vectorial sum around any closed path is always equal to what? Is always equal to 0. So this is the note you have to make. Okay. So here the note is nothing but the vectorial sum of all the vectors. Vectorial sum of all the vectors around any closed path. Around any closed path is always equal to what? Is always equal to 0. Is always equal to 0. Okay. Okay. So if you are moving, whenever you are moving around this closed path, if you are moving along the direction of the vector, take it as positive, and if you are moving against the direction of the vector, take it as negative. So add up all those vectors and equate it equal to 0. Okay. So from here, what you are going to get? So start from here. So if you are moving in clockwise direction, let us assume you are moving in clockwise direction. So then what you are going to get? So a bar plus b bar, right? So a bar plus b bar plus c bar, right? And here you are moving against the vector, so you are going to get minus e bar. Here you are moving against the vector, that is minus d bar, is equivalent to what? Is equivalent to 0. So therefore the expression for c bar is equivalent to what? E bar plus d bar minus a bar minus b bar. So this is the expression for c bar. Okay. So here the expression for c bar is not important. What is important here is the vectorial sum around any closed path is always equal to what? Is always equal to 0. So that is the main important point here. Okay. So that is the note. So this note is important here, right? Now if you observe our previous, that is triangle law and parallelogram law of additions, if you observe this one, so see here, so you have started from this point, yes or no? Okay. So you are moving along the direction of the vector, so that is a bar. Next you are moving along the direction of the vector plus b bar. Next you are moving against the vector, that is minus c bar, is equal to what? 0. So around this closed path, the vectorial sum around this closed path must be equal to 0. So from here what you are going to get? C bar is equal to what? A bar plus b bar, isn't it? Okay. So here also you can take this closed path here, you can take this closed path. So start from here. So if you are moving along the direction of the vector here, so you are going to get f2 bar, and here it is f1 bar, right? And here you are moving against the direction of the net force, so that is minus f net. So this must be equal to what? This must be equal to 0. So therefore the net force is equivalent to what? Is equivalent to f1 bar plus f2 bar, isn't it? Okay. Okay. Similarly, if you want, you can trace this closed path also. If you want, you can trace this closed path also. You are going to get what? You are going to get the same result. So f1 bar plus f2 bar minus f net. So that is f net is equal to f1 bar plus f2 bar, right? Okay. So here what is important here? The net, the vectorial sum of all the vectors around any closed path is always equal to 0. So this is very, very important, right? Okay. 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 So next year. So we have seen here the graphical approach, the addition of two vectors, graphical approach we have seen. So now we try to develop the formula. For addition of what? Addition of any two vectors, that is analytical approach. So it is very simple here. It is very simple. See here, just I am trying to develop the formula in order to add any two vectors. So that is analytical approach. Okay. Okay. So see here, it is very simple. If suppose I am having the vector, let us say this is f1 bar, and here I am having another vector, let us say f2 bar, right? The angle between these two is theta. right? Now, what is the resultant force direction here? If you want to determine the resultant force direction, you can apply the parallelogram law of forces. Yes or no? So, just draw the parallel line to F1 bar and draw the parallel line to F2 bar, right? So, this is F1 bar and this is what? This is F2 bar. Okay. So, the resultant force will be like this. This is the resultant force, or I can say this is the net force. So, net force or resultant force is going to act in this direction, right? Okay. Yeah. So, now see here. So, I am just extending this F1 bar here. So, along this line you are having F1 bar. So, just I am extending this F1 bar like this. I am just drawing a line like this, right? Okay. Now, see here. So, if I want to determine the component of F2 bar, so this is F2 bar here, this is F2 bar, okay. So, this is F2 bar. I want to determine the component of F2 bar along this line, So, how I can determine the component here? So, in order to determine the component of F2 bar along this line, what you have to do? Just drop your normal from the head of F2 bar onto what? Onto this line. So, then the distance from here to here, will give you the component of F2 bar along this line. Right. So, now what is this component here? Now, first of all, tell me what is this angle? See, the angle between F2 bar and F1 bar is nothing but what? Theta. Now, here you have drawn the parallel line to F2 bar and this line is along F1 bar. So, what is the angle between F2 bar and this line here? This line is along F1 bar. So, it is just like a angle between F2 bar and F1 bar. Yes or no? So, the angle between F2 bar and F1 bar is theta, and here you have drawn the parallel line to F2 bar and you have drawn a line along what? F1 bar. So, here also the angle must be what? Here also the angle must be theta, right? Now, from this right angle triangle, right angle triangle. So, from this right angle triangle, right? So, this is nothing but adjacent side. This hypotenuse side magnitude is F2. So, the distance from here to here, this adjacent side will become what? Will become F2 cos theta, right? Okay. Yeah. So, now what is the total distance? From here to here? What is the total distance from here to here? Is nothing but what? Is nothing but F1 plus F2 cos theta. The total distance from this point, from here to here, is nothing but what? Is nothing but F1 plus F2 cos theta. Now, if you observe, if you consider this bigger triangle here, that is F net, right, and this one, right, and this one. Okay. So, if you consider this bigger triangle, so F net is nothing but the hypotenuse side and adjacent side is nothing but F1 plus F2 cos theta, and what is this opposite side here? So, this opposite side is nothing but what? This is F2 cos theta, means this is nothing but what? This is nothing but F2 sin theta. Yes or no? See, from this right angle triangle here, from this small right angle triangle, this is F2 cos theta, means this will be what? This will be F2 sin theta. Understood? Now, for this bigger triangle, right angle triangle, this hypotenuse side is F net and this adjacent side is nothing but F1 plus F2 cos theta, and this opposite side is nothing but F2 sin theta. Right. Now, you can easily determine the net force or not, the magnitude of net force. What is the magnitude of net force here? Tell me. So, the magnitude of net force is equivalent to what? Okay. The magnitude of net force is equivalent to what? Hypotenuse side is equivalent to what? Is equivalent to square root of adjacent side whole square plus opposite side whole square. So, that is you are going to get F1 plus F2 cos theta whole square plus what? Plus F2 sin theta plus F2 sin theta whole square. So, if you do this, what you are going to get? Tell me. You are going to get square root of f1 square plus f2 square cos square theta plus 2f1 f2 plus 2f1 f2 cos theta plus what? Plus f2 square sin square theta, f2 square sin square theta. Now if you observe here, f2 square cos square theta plus f2 square sin square theta will result in what? Will result in f2 square. Yes or no? f2 square cos square theta plus f2 square sin square theta is nothing but what? F2 square. So what you are going to get finally? So the magnitude of the net force, is equivalent to what? Is equivalent to square root of f1 square plus what? f1 square, and f2 square cos square theta plus f2 square sin square theta is nothing but f2 square. So f2 square plus what? Plus 2 f1 f2 cos theta. So here f1 and f2 are the magnitudes of f1 and f2 vectors. Understood? And theta is the angle between the two vectors. So if you observe here, the net force F bar is equivalent to what? Square root of f1 square plus f2 square plus 2 f1 f2 cos theta. So that means it is depending upon what? It is depending upon the angle between the two vectors. So theta is nothing but what? Theta is nothing but the angle between f1 bar and f2 bar. Yes or no? Okay, the angle between f1 bar and f2 bar. So here f net is nothing but what? F net is nothing but the magnitude of f1 bar plus what? F1 bar plus f2 bar. So if you observe, the magnitude of f1 bar plus f2 bar is depending upon what? Is depending upon the angle between the two vectors. Right? So this is the analytical approach, or this is the formula in order to determine the addition, the magnitude of the resultant vector here, right? So whenever you are adding two vectors, if you want to add two vectors, so this is the formula you have to use, right? Okay, so this is analytical approach. Previously I have explained the graphical approach also, right? Okay, okay. So I hope it is crystal clear. So this is the way in order to do the addition. Right? So this is the way in order to do the addition of any two vectors. And here one more point I want to specify, that is note. Okay. Okay. So now if I consider a vector a bar, so how you are going to represent this vector here? So this vector is going to have both magnitude as well as what? As well as direction. So the length of the vector will give you the magnitude, and this head of the vector will give you the direction, isn't it? So I can represent this a bar is equivalent to the magnitude of a bar multiplied by what? Multiplied by the unit vector along a bar. Right? Okay. So this will give you what? This will give you the magnitude of the vector, and this unit vector will give you what? Will give you the direction of the vector. So keep one point in mind, that is the unit vector will always gives you what? Will always gives you the direction of the vector. Right? So here if you write AA cap is equivalent to what? A bar divided by what? Magnitude of a bar. So this AA cap is going to give you the direction of the vector. So how to determine the direction of any vector here? Take the vector divided by its magnitude. Take the vector divided by its magnitude, then that is going to give you the direction of the vector. So always the unit vector will give you the direction of the vector. So in any problem, if they have asked to determine the direction, then you have to determine the unit vector. How to determine the unit vector? Take the vector and divide it by its magnitude, right? Okay, so this point also very important. Okay, so whatever we are studying here, we are going to apply all these things in our subject, right? Okay. Okay, just I am trying to make you familiar how to deal with what? How to deal with the vector quantities, right? Okay, so once you get familiar with vector quantities, then you can easily understand this subject in a crystal clear manner, right? Okay, so in this lecture we have studied about what is a scalar quantity and what is a vector quantity, and also we have studied about the addition of vectors, how to do the addition of vectors. Understood? Okay, so I hope this is crystal clear, right? Okay, so in the next lecture we will see how to determine the component of one vector along the other, and also we will see how to do the vector multiplication. What are the different types of vector multiplications we are having? So those things we will see in the next lecture, right? So with this we have completed this lecture here, right? So thank you for watching this entry app. So with this I am completing this lecture. So we will meet in the next lecture. So until then, take care, bye bye, and thank you for watching this entry app, right? Okay.